Good morning, everyone, and welcome to the first session of the Getting Close to the Nucleus workshop. The first speaker is Gilles de Weis. He's an assistant professor at the Radboud University in Nijmegen in the Netherlands, and he's written much of the NMR code in VASP over the past 20 to 30 years. His research interests lie in modeling the behavior of solid-state systems in magnetic fields, and he'll be talking about the projector-augmented wave, the PAW approach in VASP, and the calculation of several magnetic properties with it. So I will give the stage to you, Gilles, and I'll turn my video off. Can't wait to hear.
Thank you very much. Thank you, Chris. Then we're going to start with the first session here, getting close to the nucleus. And well, we have to go close to the nucleus. So first we have to talk a little bit about the PAW method. But before doing that, let me just show you the names of a few people who have actually contributed to the NMR corner of VASP in one way or the other. And let me now go to part one. And so the first thing is a short outline of the PAW method in as far as we need it. Because we are going to look in the vicinity of the nucleus, we need to have the detail of the orbitals near the nucleus, and that is why you need PAW. And I will give a brief summary in a moment of the details, but it doesn't go in all the full detail of the PAW method. That would be a different workshop. After that, we will talk about the gates including PAW, which you need to calculate NMR shield. Today, it will be mostly the theory side of things. Tomorrow, it will be more the practical side of things. Let's start with the basic. Going towards the PAW method, first, of course, there are pseudopotentials and plane waves. And in VASP, the basis is a plane wave. And here you see the top lines, you see the block states, and the block states which are expanded in plane wave with the coefficients here and the expansion coefficients. And everything below the kinetic energy cutoff, EN cut, is usually included in the basis set. You want to have this EN cut as small as possible to have an efficient calculation as possible. But if you come near the nucleus, here you see, for example, the carbon 2s orbitals. You see the radial plot of the orbital. When you come close, the red curve here, you see it starts to oscillate a lot because this is the 2s. It has to be orthogonal to the 1s, so it has this node over here and this rather strong oscillation. If you want to expand that in plane waves, you need high frequency components over here and you get a high kinetic energy cutoff. And so the traditional solution, already long time in the past century, was to make pseudopotential. And what would you do with the pseudopotential? You would take such an atom, for example, and you would freeze the core. So in the carbon case, the 1s orbital. And then what you would do, you would construct an orbital, which is a pseudized orbital, which is the blue one over here, which is smooth, much smoother than the red one. And at the outside of a certain cutoff radius, it's exactly the same as the real all-electron solution, but inside it is much smoother. If you have this orbital, in this case for an eigenstate, could make up a potential that actually gives you this orbital instead of the red all-electron orbital. This is called the unscreening step. And then you get a smooth pseudopotential that has this blue thing as an eigenstate, for example. Of course, there are all kinds of tricks to do this accurately, and we will see a few of those also in the next slide. The key part here is you replace it with something smooth. And when you do that, the red message over here is detail of the orbitals near the core in the core region is lost. So you don't know anymore what the orbital here looks like. And you want to go to the nucleus which sits over there. So that is a problem in principle. Okay, now here you see the same thing as in the previous slide, but now in words, the recipe to make a pseudopotential. And you first do an all-electron calculation for a reference atom in a certain state. And then you select the energies where you're going to make the pseudopotential. And those energies are typically numbered 1, 2, 3, 4 with the energy levels, but they're also labeled with the angular momentum channel and the big L over here. Okay, so you have selected those energies and the orbitals, and then you replace the orbitals with pseudo-orbitals, which are smooth and which are continuous at the cutoff radius, and outside the cutoff radius, they are identical to the all-electron ones. And traditionally, people choose this to be a norm-conserving construction, which means that the pseudo-orbitals are normalized as, of course, the all-electron orbitals are normalized. There is just 1 or 2 electrons in there. The pseudo-orbitals would also have that. And when you do that, you make a good quality pseudopotential. You get good scattering properties. And then in the fourth step, you cook potentials that actually have these new orbitals as eigenstates. That's the unscreening step. And then you get something, a potential that looks like this. It's a local potential plus short range corrections to that, which work with projector functions over here and strength parameters. And these I's and these J's, this labels again the angular momentum channels and the energies. And this thing here, this local potential, has the long range part. It has the Coulomb tail in there. So all this is short range within a sphere near the nucleus. And doing this, of course, is very difficult. If you take the wrong energies or core radii, you get ghost states, which are bound states with nodes below the ground state. So that is really nonsense. You get bad scattering, etc. So try to avoid doing it and use good ones made by somebody else. Here you see it again. Again, the message that you lose information near the nuclei, which is fine for most properties. If you want to calculate chemical bonding, you need what happens in the range in between the nuclei, and you're not really care so much what happens at the nucleus itself. Okay, for magnetic materials, you have to be very careful, but even then, you can describe this. But for NMR, this really goes wrong because you need to know the fields at 0, and they are dependent on the shape over here. So this in principle doesn't work. Well, it's not as strict as that. If you take very, very hard pseudopotentials with this core radius far to the left with high cutoff, then in the top part of the periodic table, you can get somewhere. Okay, but you need this detonating nucleus, and in the projector-augmented wave, this of course comes automatically, although you pay the price of having a frozen core. Now we go to the next slide, where there is a cartoon of how the PAW method actually works. PAW means projector-augmented wave method, so it's all electron, but it is supposedly as simple as a pseudopotential method. In the strict sense, it is not a pseudopotential method. The key approximation here is that we can relax in part. We can unfreeze part of the core electrons and also treat them as valence electrons. Okay, now let's see what we have over here. We have a cell in which we have the blue part, which is of course the orbitals. We have the red parts, which are near the nuclei. And here there is a nucleus. This is the nucleus over here. There's another one over there. And in this region, we have this very strongly wiggling orbitals because of the orthopolarization to the core orbitals. And what you can do, this exact picture, you can represent it by, say, pseudo orbitals, which are smooth, which we can represent it by plane waves. And you have the smooth parts also in here. So it's kind of this pseudo potential like picture where you get smooth orbitals out. But you have to, this is not what you have here, but in this PAW method, you can correct. You can remove quasi the part which is in the blue spheres, the smooth part, and you can replace it by the actual thing with all the electron details, so with all the wiggles in there. That's the idea. It's in the next slide. It is actually written in formula. These all electron states here, it says are reconstructed, representing a pseudo by an all electron partial wave, which means you get the correct shape of the station in the nucleus. And this is done in one center correction. And this is a center, and this is a one center correction around it. And this is another one. This method is done by Blugel, and he published it in 1994, and it is very widely used. So now in formula here, you see exactly the same thing. You see, but now is a linear transformation. These are the pseudo-orbitals, so the blue part. These here are the orbitals you want to subtract out, also essentially blue. And these are the all-electron detail ones that you want to add. It's labeled here with R, which is the atomic nucleus site you are in, and this is the angular momentum channels, etc. And what you do is you have your plane wave solution, you work on that with the projector function. With that, you get the coefficient, and that coefficient tells you how much you have to subtract out and add in the electron orbital to restore the full Gaussian orbit. Okay. So in order for this to work, this is important. You need to have sometimes a complete set. You have to be able to expand everything in these partial waves and these projector functions. So that it leads to this requirement, which very often we assume is true, but is only true to some degree of approximation. This is all done in an atomic calculation, where the frozen core electrons are then indeed removed from the problem. And once you do this, you go through all the calculus, you finally get a pseudo-Hamiltonian, which looks like a pseudo-potential problem, and an overlap matrix. So the Hamiltonian is just working on the Gaussian orbitals on the plane wave grid, gives an eigenenergy times the orbital, but here you also get an overlap matrix. The overlap matrix you see over here, which in principle is just the identity, but if the norm of the, say, the pseudo partial waves and the real partial waves are different, this difference is not zero, you get an additional term, you get an overlap. In the old-fashioned norm-conserving pseudopotentials, you would not get this because then this would equal this, and it would all go to the identity. Okay, so here again, the cartoon with formula that belongs to it. This one is over here. What you subtract out sits over here. And what you have to add with all the electron detail is the red stuff over there. Now you have a very exact, very good approximation of the orbitals. Now, this stuff over here lives on the plane wave grid. This is a smooth thing, and you can then Fourier transforms of it and play all kinds of games. This stuff over here is not on this plane wave grid because this plane wave grid is rather coarse and this has all these details. Certainly it has it over here. So you represent it in a different way. And you represent this as a product of a radial function times spherical harmonics. You will do the same thing over here. And those partial waves, certainly the all electron, the all electron ones, but also the pseudized smooth ones are represented inside the spheres using a radial grid in combination with spherical harmonic. And this radial grid is logarithmic, so that means that it gets finer and finer and finer the closer you get to the nucleus. And typically you go to, say, 1/100th of an angstrom close to the nucleus or even closer, but that is sort of the distance you have to think of. And then the grid gets very, very fine. And the further you move outward, the coarser the grid gets. But outside of the spheres, you don't need it anymore because there everything can be represented on the plane wave grid. Okay, and this red stuff is crucial to restore the all electron detail. Good. So now we have seen the orbitals. We talked also a little bit about the Hamiltonian, but we also have to know what a typical operator does. And with an operator, we want to measure something. Maybe we want to measure the field somewhere, or we want to measure the current somewhere. So how does that go in the PAW method? If the operator is sufficiently nice, so it's local or semi-local, but not truly non-local, you can represent it in this way. The real operator, for example, a position, and we will see an example in a few moments. You can replace it by a pseudo operator, which actually is the real operator that you see over here, plus some correction. And that correction term is again a one-center thing, which goes over all the PAW spheres. And so you sum over all the sides, all the PAW sphere, all the nuclei. You have again your projector functions, but in here now you have matrix elements of the partial waves with the operator of the pseudo one, so you subtract that out, and of the all electron ones, which again give you your resolution in the nucleus. That is the red thing over here. And you can have a shorthand notation for this. The pseudo operator is the real operator plus a one-center all electron correction minus a one-center. Good. And now you operate with this on some plane wave expansion. And that plane wave expansion, of course, has all the variational freedom in the expansion coefficients in plane waves. Here you see how an orbital goes to a certain K point. This is phase vector for the K point. This is the cell periodic part of your orbital. And then the cell periodic part of the orbital is again expanded in plane waves. And these are the coefficients. And all the variational freedom is in there. And so you don't have additional coefficients for your partial waves. That all comes along with this. And this is again your traditional plane wave basis set. It is truncated. That only plane waves with the kinetic energy below the cutoff energy, EN cut, are included in the basis set. So you calculate the kinetic energy of the plane waves, and it should be below some cutoff, which is typical for a pseudopotential or for a podcast. Okay, so that's how you calculate an operator, the expectation value of an operator. So now here is just an example that is not so important for our case of getting close to the nucleus, but just to see how it goes. Suppose you want to calculate the kinetic energy. Then you see here the kinetic energy. Here you see the operator. Well, there is some minus, but we've thrown it on the other side. And you just calculate the matrix elements with your pseudo partial waves. With your pseudo orbitals here. So these live on the plane wave grid. You get occupation numbers with it, the weights, and you sum here over all the occupied orbitals on the plane wave grid. But then you also get these one-center corrections with the projector functions. And if you just rewrite a little bit, it's very simple. You make from this term, you make the three separate sums. Then you first get the pseudo plane, the plane wave contribution. That's the first one. And then you get the one-center corrections, the all electron ones minus pseudo partial wave ones, and then you get this stuff over here. This measures how much of a certain cone-jump state is on this side in a specific channel. So these are the projector functions. And this gives you a matrix, a kind of a density matrix, usually over here, which depends on the side and on all the channels, on the left side and on the right side. And now you see we have a plane wave contribution and two one-center contribution. This is again the shorthand that you do. For the first term, you can very easily calculate it with the Fourier transform. If you do that, you actually have that this thing is this Nabla operator is diagonal in the Fourier space. So that is very quickly done. And this one center that we have to stress again, they are evaluated, these things over here, you only do once. You only have to do it once at the beginning of your whole calculation because you know these partial waves. You do that on the logarithmic grid inside the PAW sphere, which makes things accurate again. And each time you iterate in a big calculation, you have to update these rows with these projector functions over here, which of course you can do on the plane wave grid. Typically you do it in the reciprocal space. You can also do that in real space. Because these projector functions are short range. They are within a certain sphere. Okay, so that is kinetic energy. And it now seems all rather straightforward and simple. It's always the same recipe. And this is actually what we need for the whole NMR story that is to come. But just to say, life is a little bit more complicated. Just we glance for 2 slides at the total energy. The total energy, again, has a plane wave contribution and 2 1-center corrections. You subtract a pseudo, you add another electrons. And the plane wave contribution is written down over here. And you see here, well, what we already expected. This is the kinetic energy part. But there is also an exchange correlation contribution. There is an Hartree contribution of the electrons talking to each other. This here is the pseudopotential-like construction, where this is a pseudopotential talking to the soft charge density. And then there is, of course, a bare ionic contribution. And now you see new things over here. You see this tilde here. This is the charge density. And for charge density here, and with the tilde is the pseudo charge density. That's not new, but with the hat here, you see other things. These are things which are present in the code to handle all kinds of electrostatics. This is the compensation charge density, which gives you the correct number in the PAW sphere, because the correct number of electrons is, of course, not there, because these partial waves are not normalized to 1. And you also see core charge densities. That's we have had removed that previously, but you have to add that, of course, in the exchange correlation contribution. Not in here, because it goes effectively via this effective charge over here. Okay, but this is only the plane wave contribution. And there are also 1-center contributions, pseudos 1 and an all-electron 1, where the exchange correlation comes back again, the Hartree comes back again, all as 1-center contributions calculated on this logarithmic grid. Yes, and it's important to notice here, so this is the all-electron one, here we get the real density of all the valence orbitals plus the real density of the core added. Again, you see the detail comes back here. And the same you have in the Hartree contribution. Okay, so this is the general picture for that's the energy. We will need later also how the Hamiltonian that belongs to this looks like. So we get a pseudo Hamiltonian in this method, which is kinetic energy, something effective, and again, 1-center stuff, which 1-center corrections. And these two are the important ones for us. And we get an overlap problem. We've already seen that with this Hamiltonian. You get an overlap matrix over here, which is the identity plus these deviations from the norm conserving conditions. And these are the key references. We've already seen the Blugel paper, and this is on how it is done inside VASP. So that's the basics of the PAW method. And now what we're going to do is we're going to first talk a little bit about electric field gradients. Electric field gradients is something that you can rather easily calculate with the PAW method, and that you can measure with NMR, that you can measure with NQR, that you can measure with Nussbauer. But now we're just going to talk about this tensor itself. It is about the electric field gradient at a specific nucleus. So you see here we go to the nucleus site and we take the double derivative of the potential. And the first derivative of the potential is the electric field, and the second derivative of the potential, that is the electric field gradient. So you do one differentiation, you get a vector. You do it twice, you get a 3x3 tensor, which alpha and beta here are, for example, the Cartesian indices. While this own thing over here already makes electric field gradient tensor, this thing over here takes care that it is traceless. So it somehow adds the trace and subtracts it. And in NMR, people always assume, or almost always assume, that the tensor is effectively traceless, because it is not, but the effect is so small that you can hardly see it. And if you look over here, you see the Laplacian working on the potential. So you see Poisson's equation getting here. And essentially what you're doing here, you're calculating the charge density. Subtracting this out, is saying essentially that you say there is a zero charge at the origin, which is not true, but it is good true in a good approximation for this property. Okay, so this is just property you want to measure. So you can do it in the PAW way. You get something on the plane wave grid, which you see over here. And then you just have put it in the plane wave expansion, and the derivatives just bring down G twice, and you get 1 center corrections. And the 1 center correction have this form. That's a YLM times something radial. And this thing only has L equal 2 terms that actually contribute. And for the PAW method, this was derived in 1998, how to do this in this paper. Okay, so this is the formulas. So it in principle is rather simple. You don't have to do anything additional. You just do a self-consistent calculation, and after you have obtained all your orbitals and your potential, you just calculate this and you get your field gradient best. But you also have to represent it. And how do people do that in practice? Well, they have this tensor. This tensor, I go back again, by construction is symmetric. And it's also traceless, but it is symmetric by construction. So you can always diagonalize the thing. So you can bring the thing to principal axis. And a principal axis system, all the off diagonals, so where alpha and beta are different, all those elements are 0. So you only have 3 different ones. On the diagonal x, y, y, and z, z. And because it's traceless, we also know that the sum of these 3 is 0. And now you're going to order the 3 principal components in such a way that VZZ is the biggest one, and YY is the smallest one, and XX is somewhere in between. And then when you do an NMR experiment, you see VZZ, and you see something which is called the asymmetry parameter, which is the difference between the other 2 components divided by VCZ. Because this one is the biggest in absolute terms, this asymmetry parameter is always smaller than 1. You can calculate it back a little bit to this stuff. Only in NMR, you cannot see the sign of this. So that is a little drawback. And people also, they don't report this VCZ. They typically report something they call CQ. And CQ is calculated in this way. This is Planck's constant. This is this VCZ, for example, in volt per angstrom squared or something like that. And this thing over here, this E times Q, is the nuclear quadrupole moment. So it's different for each isotope. There are many isotopes that do not have a nuclear quadrupole moment. For example, carbon-13. And if it is not there, you can actually calculate VXCZ, but you cannot measure the CQ because this thing here is 0. And so you need quadrupolar nuclei to actually see this. You need this in order to calculate the CQ and compare to experiment. And there is a very nice, very big compilation. The most recent one is from 2017 by Pico. You can look over it here and over here. This is also a nice list with an overview. So you can always look up what these things are, and they're still being improved. So they're not 100% sure, but they're pretty good. If you want to do this in VASP, you just do a self-consistent calculation, and then you switch it on in the in-car with L EFG equals true. And then you get the whole tensor, and you get also the principal axis, and you get all the components in the principal axis systems for all the nuclei. And if you give these quadrupole moments, it also gives you the CQs. So this you put in a millibarn, and this you get out in megahertz. In megahertz, because here you divide by h. This sets somehow the scale in which this is calculated. Where you have to be very careful is that you don't do this with the default settings, because then you will get nonsense for sure. Your convergence has to be really good, certainly a few order of magnitude better than usually. So E diff has to go down quite a lot. And you also better test your cutoff energy carefully until you get a converged result. This with the exclamation mark is very important. And now why these EFGs are important. The first statement over here, they are extremely sensitive to the structure. So you change the structure a tiny little bit and the EFG often goes quite a lot. In this old paper by Petrelli and Blugel and others, they showed this very clearly with titanium dioxide, where here you see a change in the positional parameter of almost nothing, change the VCC by 40%, so the big component. So the CQ would change by 40%. So you need to be very careful to get good converged results. Conversely, if you get good numbers out, it tells you really something about your structural model, that your structural model is probably very good. Now here the test on rutile, so the literature data, this is full potential, LEPW, so this is what should come out from your DFT calculation, in this case in the LDA. Below here you see the experiments, so that matches pretty well, but this is the reference. The PAW method by Petrelli came here, and then we started to do this. This is just a standard titanium potential, which only has 4 valence electrons. And you see it's really, really very bad. So you need here also to consider the semi-core. You have to unfreeze all the 3s and 3p's with these guys over here. And then you already get a much better result. So this is, you can do with the standard podcast, one of the standard podcasts, but from the distribution. And then if you really try to make the ultimate potential, you can push it a little bit further and you can get quite close to the LAPW result. Right? And here you're almost on top. But the take-home message here is an important one. You need good PAW data sets, complete, and often you need semi-core states in there. And what you saw over here, you have to be careful with your convergence criteria. You really have to be very careful with the EDIF and the EN cut and the K point. But not as so sensitive to the K points in a semiconductor like titanium oxide. If you go to metals, where NMR becomes very difficult, but you could, for example, do that with Mösbauer, then this becomes also really tricky. Okay. NMR and QR Mösbauer are typical experiments with which you can get these field gradients. It's traceless and symmetric, traceless by construction, symmetric by definition. And in the principal axis, it is characterized by the biggest one and the eta. You need a very good quality ground state density. And so you only need to do an SEF, nothing more than that, but it needs to be good. You need completeness of projector functions, plane wave, projector functions and partial waves, semi-core you have to consider, and it is extremely sensitive. And what will become in the second part of the lecture, at comparison to real experimental systems, this is also sensitive to dynamics. So if things start to move inside the real material, then these EFGs and also the shieldings can be impacted quite a lot. And you have to additionally model that example with molecular dynamics. But this is not what we want to talk about today. We want to keep it as clean as possible about the properties. Now we go back to PAW again, but now to gauge including PAW. And this has to do with calculating chemical shielding. So first, briefly look at what the chemical shielding tensor is. Tomorrow we will look in more detail. But here you see a definition that we will work with. So we start from this red thing over here. What do we do here? What we see here, we have a shielding tensor, which is specific for a certain site in the system. Big R is where the nucleus is sitting. You apply an external magnetic field, which can have 3 Cartesian directions, and you measure the electric field at the nuclear position. So very close to the nucleus, on top of the nucleus, in fact. And that also has 3 Cartesian components with the alpha index here. So this thing is a 3 by 3 quantity, and it is linear in a very good approximation. So we want to get this derivative over here. Because we want to have a shielding, we have to put a minus. Everything which goes against the applied magnetic field, we measure as something positive. That's the concept of shielding. You also see another definition over here. we will briefly mention that probably tomorrow. But this is not what we should focus on here. This is the traditional way of looking at it. This is also what happens in the actual experiment. We apply a magnetic field, we measure the induced magnetic field. We want to get the proportionality between those, and that is expressed in the shielding tensor. And indeed here it says it mimics the physical process. We have a uniform magnetic field. We call this either B0 or B external. The experimentalists always talk about the B0 field. We apply this. When you apply this to the material, you induce currents in the material, quantum mechanical currents that flow in there without any resistivity whatsoever. And these currents, they give rise to a new magnetic field. Those currents induce magnetic fields everywhere, but also at the nucleus. And at the nucleus, you can actually sense that with the Zeeman effect of the nucleus. Again, we will talk about that too. But the nuclear spin feels these fields at the nucleus, and this is the induced field. And this is also how we're going to calculate this. This is a recipe, and this works for insulator semiconductors in the GIPAW in absence of spin orbit coupling. We will come to that at the end of today's talk. Again, it's summarized. It's specific for each nucleus, depends on the Cartesian directions of the applied field and of the induced field. So there are 9 elements, and in principle, there are 9 different elements. Again, tomorrow we will see in practice, it's not like that, but in principle, it is like that. And this tensor has 9 independent elements. And here in summary, you see the strategy to calculating. You apply a B0 field, you put it in the Hamiltonian, that gives rise to an induced current. There was no current initially, now you get a current. That current you throw into the Biot-Savart law, and you can calculate the induced field by this current at any point in the material, and you're going to do that on the nuclear position. Then you have the ratio of those two, and you will do this in linear response, and then you have shielding. Now, here is exactly the same story, but then only in formulas. So we're going to bring the system in an all-electron story. So this is about the basic idea. This is not the actually implemented formulas, but we bring it into a uniform magnetic field, and we take the vector potential of that field in this way. That we always do. This is the symmetric gauge. It's the vector product of the external field and the position divided by 2. That is your vector potential. So it increases linearly with position in space. And when you have such a field and its vector potential, how you put it in the Hamiltonian? Well, you modify the kinetic energy. So this is the momentum operator, but you now add an additional contribution proportional to the vector potential. And I have to apologize a little bit about units. Occasionally you see CGS Gaussian units, like here. Occasionally you will see, you've seen in the past, today you see SI units, but here it is in this Gaussian units. Okay, now you have this, so now you can solve the problem again with this applied potential, and you find your Grandjam orbitals of your system. And with those Grandjam orbitals, you can calculate the current. And you have 2 contributions, a paramagnetic one and a diamagnetic one. The paramagnetic one just comes from the gradient of the states. So it's also a momentum operator-like expression. And the diamagnetic one comes from the vector potential times the density. And it depends a little bit on the choice of A, because A is in principle not unique. Any A that produces the same B is allowed. There is gauge freedom for this A. It depends on your gauge choice, what is paramagnetic and what is diamagnetic. Now you've done this. Of course, the sum of those things is gauge invariant. You can change the gauge here to something else, but you can still get the same current density out, only differently distributed over paramagnetic and diamagnetic terms. But anyway, you have the current, you put it in the PAW law that you see over here. So you integrate over all space where this current is living, and you look at a certain position big R, and you want to calculate the field there. Then we do it like this. And this is the whole electron story. So in principle, you do it like this, but there are many, many technical difficulties that come in. They have to do with the plane wave basis, which necessitates PAW. PAW is in trouble. That's why you get gauge including PAW. And you have the periodicity of the solid state. And you already see this thing is not periodic because it increases with position. And so there are all kinds of things going on. And now let's first look at GIPAW, at this gauge including thing. What is this about? Here you see it. What happens if you take a system and translate it in a magnetic field? And then the potential here, this is where the nuclei are sitting, this is shifted by some translation vector. But you keep the same external field. You just translate your whole system. In principle, you would say you translate your whole system, nothing changes. That is what you would call translational invariance. But this is not really true, almost true. What happens is that when you translate your system, you get this green guy over here. You get a phase vector. Of course, a phase vector in principle you can't measure. The charge density that belongs to it, multiply this phase vector with this complex conjugate and it's gone again. But it is there anyway. We have to consider this. And why that is there, you can see a little bit in the next lines over here. Here the phase vector is needed, it says, to align the full momentum operator with the translated orbital. That's actually what is happening over here. What is going on here? Apply this, so this thing over here, we apply it once on the translated orbital. So with this already in, then you get three terms, this one, that one, that one. And you pull all those terms together. That happens over here. And then you see you have two terms with a vector potential. You can move them together. You can merge them into this one term over here, where we now have A0, R minus T. And the orbital on which we're operating also is at R minus this translation vector T. So this has R minus T, this has R minus T. So you know that if you operate with this on this thing over here, you get back the orbital at R minus T. But in order to get that, you need this over here. And this was constructed because of this phase vector, which now we also have up front. So this is consistent. This phase vector is there. And when you do PAW, you kill this, you damage this by this nuclei that you move about, but you don't account for the phase vector. So what the solution then is you bring in these phase vectors in the projector functions and in the partial wave of your PAW method. And that is what is called this GIPAW, which was introduced by Pickard and Maury in 2001. And here you see it in a formula. Let's first read the text. In a formal sense, the phase change of the eigenvectors upon translation is restored by a twist of partial waves and projector functions. And that's all in red over here. And so over here, you twist one way, and over here you twist the other way with a minus. Here you have the plus. And you can write it either as the vector potential at the side, or you can expand it and say, okay, what is that? Well, that is R cross B divided by 2. And that's 2 over there. In terms of orbitals, it looks, so of operators, sorry, it looks like this over here. The operator transforms to its GIPAW transform now with the bar instead of the tilde. You get stuff over here. Here you get the phase vector. Here you get the opposite phase vector. And in the partial wave matrix elements over here, you don't only have the operator, but you have these phase twists, one way and the other way. And here you see how big it is. Okay, and now I first go to the next slide because there you actually see what it does. And what this does is, in an informal sense, it says here the gauge origin is locally shifted onto the nucleus in each PAW sphere, so the strength of the perturbation is minimized. That is the actually numeric advantage of this. And you see it outlined over here. So hand waving gauge including. Here you see the vector potential. It just goes linear with position in space and it being bigger and bigger and bigger and bigger. And suppose here is a nucleus sitting. This is position, this is vector potential. And then it feels a rather big potential here. And the further you get away, the bigger the potential becomes. But this phase shift twist, what they actually do is they twist with exactly this amount. And they bring quasi the gauge origin, this point, they bring it back to the center of the PAW sphere so that you get a rather weak potential inside the PAW sphere in the vicinity of the nucleus. So that's why you don't need very many partial waves here. If you would have a very big potential, you need more and more quasi-excited states in your PAW construction, in your pseudo potential construction, if you want to say, and your basis will, your partial wave basis will explode. And that is not what you want. That is numerically why you do this PAW trick. And this trick is, this gauge including trick. And this gauge including trick is already older than PAW in the quantum chemical world. It's called gauge including atomic orbitals. And you find this in many of the quantum chemical codes. Okay, so this is a little bit about what GIPAW is doing. So what it actually is in detail. So now we know two things. We know the recipe, how to calculate things in big lines. And we know what this gauge including thing is doing. And the whole story is, of course, much more complicated. And we're just going to zoom in on several aspects of this. The first thing is we will do GIPAW with a frozen core. Okay, that can be done. It's not so straightforward, but this is this paper. This discusses this, why you can actually do that if you choose the proper gauge. And so we are in this symmetric gauge all the time. That is important. And then you can calculate the shielding for the core electrons separately in a very good approximation. That's the first bullet. The second bullet is, and we already see this, well, you see this over here. A increases with position, so it doesn't fit into the periodicity of the cell. But in perturbation theory, you can get away with it. That's the second point to note. And then third thing is comes also back later, so we can skip over this. And we're going to do perturbation theory. That means there is a green function, but we can speed up that a lot. What is also important is that everything in this whole GIPAW thing can be cast into a formalism where you only have differences in positions. And that is important because the position operator in periodic system is something very difficult to define. Since it's not very well defined, but with differences it actually is. But still, you want to do a calculation not in a supercell. You want to calculate everything in the primitive cell of the system you're interested in. And that can be done with this funny trick over here, introducing K-points, stars. We will talk about that in a bit more detail later. But it is important we can go to a primitive cell and then we pay a price. And we see a moment later why that is. Our Brillouin zone becomes more complicated. Instead of the usual grid in there, we can charge stars on the grid, small shifts. And that means that instead of doing 3 response calculations for the magnetic B0 field in 3 different directions, we have to do 21. Then there are other problems. We will also see them back in a moment. Para and diamagnetic current densities, you can see them over here, this one and this one, also on the plane wave grid even, they have different convergence rates, which means that if you are in another position, your shielding tensor doesn't converge at the same rate. This can also be cured so that everything becomes invariant upon translation. The shielding becomes a variant of translation because of this and because of the GIPAW structure. That is all which is in this GIPAW. This is the big picture. We step through this very quickly now, and then in the next one we go slides. We go a little bit slower, but we cannot read everything. Then you just have to read the original papers where this is very clearly explained. Another thing we have to consider is that we have to take care not only of currents flowing in an infinite lattice that give rise to shielding, but also our crystallites have a finite size. And so we have to take care of currents flowing on the surface. And in order to do that, you need to get a magnetic susceptibility. That's another thing which is in slower steps. So instead of the big picture, step by step. And so we closely follow their approach. And so that's this paper over here. What we have in VASP is that we use for the shieldings exactly the same PAW beta sets as we use for the self-persistent calculations. So we have no special pot cards. So you have to select the proper ones, select them with care. And in order to switch this on, you just switch on LGMAG. We will see more detail on that tomorrow. We need current densities. So let's look at the operators that we need. And we already saw that. We need paramagnetic current and a diamagnetic current. But here, this is the big J's, these are the operators. And the paramagnetic one operates with P and then puts it at a certain point in space. And the diamagnetic one multiplies with the vector potential and puts it at a certain point in space. So with this projection, working both sides, we will get a density. The distinction is defined by the symmetric gauge. Yes, so it depends on which A you choose here, which part of the current will end up there and which part will end up there. Okay, matrix element of the G-transpose operators yield current density. That is true. Yeah, so the small j's. And everything lives again on the plane wave grid, and we have one center correction. So the form is like this. You have a plane wave contribution, and you have for each side one center corrections of little currents flowing there. That's one ingredient. And next ingredient is perturbation theory. Yeah, you have to do everything to first order in the magnetic fields. And you can write down the whole Hamiltonian. We're not going to do that. We're only going to notice here that the induced currents requires two things. It requires to have the orbitals calculated to first order in the external magnetic field. That's this one over here. And you need your current operator to first order in a magnetic field, which goes by the vector potential and your overlap to first. But the big challenge is this, and the computer is doing 99% of the time is calculating this first order induced current. Here you see the problem it has to solve for that. The first order induced current is a Green's function times the first order Hamiltonian working on the zeroth order orbital. And the Green's function you can write down like this in a formal sense. You have to sum over all the empty orbitals to very, very high energies in order to get this first order current. And in practice, this is of course not done like that. You can do it like that. You just have to go into the source, change one precompiler statement, recompile VASP again, and you get this. But then it becomes extremely slow, so don't do that. But the message here is GIPAW transformed operators to first order. You need all that stuff. And the work of the computer goes into calculating this. This is all the time. First do the SEF, and after that, 99% of the time goes into this. And this can be done in a formal sense with this Green's function, but we do it in a different way in practice. Then the position operator. That is not well defined in periodic systems. If you read the important papers, you can see that all contributions to the induced field can be expressed as differences. But then still, you might have to work with a supercell in which you have to have all induced currents in the whole system in one big cell. And that is not what you want to do. You want to work with the primitive cell, and there are two ways of doing that. A way which was originally used by Maury and others, but that is not what we're doing. We're following the Yates-Pickett-Maury approach, and that stands over here. And let's look at this a little bit. Here you have a difference. For example, here you sit at a nucleus, and here you have a current at a different position, or vice versa. It's a difference. And you can express this difference factor multiplied with some unit vector in some direction. And these are either the x, y, or z Cartesian unit vectors. You can express it like this over here. And you can easily see that when you start over here. If you would do a Taylor expansion of this and a Taylor expansion of this, then in zeroth order, this is 1 and that is 1. 1 minus 1 is 0. That doesn't contribute. Then you take the first order. And the first order goes linearly in Q over here, linear in Q over here. It doesn't vanish. And if you divide by 2Q, you get exactly this on the left-hand side. And then you go to the second order contribution, that's linear in Q, but you take Q going to 0, so it vanishes if you have a small, if Q comes close enough to 0, if you select a small Q that is small enough. And so what you do, you replace this by this for a finite Q, which is not really 0, but is very, very small. You can set it in your input. This is the DQ thing, but there is a default, and the default is always, well, very often is already quite good. So you typically don't have to touch this. Okay, but what can then happen here? Here you see an IQR. This form is actually the same thing as the K point in your block state. So you can move this into the K point of your block state. You can go from a K point to a K plus Q or a K minus Q with this phase factor. And so going from a big cell, you go to a primitive cell, but you pay in having to do things shifted away from your ordinary mesh in the real end. Okay, so talked about this a long time because it's important. It goes to the stars, and the stars you have to deal with in the calculation. So the current density then, because of this, gets this form, gets something which lives on the star, but not for everything you have to do this trick. There are also things which just live where they are. And so you get these stars, and you apply the magnetic fields in three directions. And so instead of one K point, you get the stars, you get twice in X, twice in Y, twice in Z, that is 6. And you have 3 external field directions, so that's together is 18. But you also have this contribution that gives it 3, together 21 response calculations you have to do. Here you see it again, these K point stars. Here you see a Brio-Hanson integration. So this would be, for example, your primitive cell in reciprocal space. And then this is the Brio-Hanson that belongs to it. And this is the gamma point. And typically you sample this with a mesh. Here it's a 3 by 3 by 3 mesh, gamma centered in this in this cell. And then you have to have all the points where the lines cross. And now you see you get stars over there. So you have to do all the 6 points plus the central points on all those stars. And you have to be careful now with symmetry, because it can be that you set up your self-consistent calculation. You do that in an irreducible part of the Brio-Hanson. VASP does that for you. But you now make these stars. And those stars should also be consistent with the symmetry of your system. Well, that's not true. If they are not consistent with the symmetry of your system, your Brio-Hanson effectively gets bigger. You cannot use the usual irreducible part. And you have to be very careful there, because it depends on how you choose your cell, how these stars are lying, because these stars are always lying along X, along Y, along Z. And in POSCAR, you can set up your primitive cell in whatever direction you like. And when you use this flag, this setting in NCAR, it effectively checks that all those stars, when applied, when the symmetry operations of the letters are applied to, then end up on stars again and not end up on stars again. And it enlarges the BON zone in order to be consistent. Okay, so that was here where we were talking about the escape point stars. And now about the para and diamagnetic currents. There we go very fast because you don't notice that this is all programmed and it is working. But even on the plane wave lattice, they have a different convergence rate with respect to bases, the paramagnetic and diamagnetic current densities. And that gives this translational invariance. And this can be cured with this famous Epson rule. That's a Maury paper in the 1990s. And here you see it. I think this is for norm conserving. But what the trick here is, this is the thing is, the trick is to have your diamagnetic current as badly convergent as your paramagnetic current at the same rate. Then you retrieve again translational invariance. And that is actually what is done. The formulas are like that and is automatically taken care of. Okay. So for the current, what we now have, we have a plane wave contribution and we have this one center corrections to it. In every PAW sphere, we have that. And now it gets even more complicated. This is too much. So we should not discuss all of that. The real point is Cartesian stars, which we already talked about, of the Q points, Q displacements, get onto all the K points into the formula. So you see that happening here, you see it happening over there. You see the indices K plus Q, K plus QI, and K plus QI also in this Green's function over here. That also connects the K point and the shifted K point. And this QI has to do something with the unit vector in that specific direction. And you go two ways. You go in the positive and in the negative way that you see over here, and you go in the X, Y, and Z direction. That makes the star again. This we have explained. But here again, stressing, you get these 21 response calculations, and tomorrow we will see how it looks like in the actual calculation. Now getting rid of the Green's function. This is the Sternheimer solver, and this is important. Once you have solved your SCF, you have a problem like this. You have an unperturbed Hamiltonian, you know all the orbitals with that, and the Grotjahn eigenvalues that belong to it. What you're going to do, you're going to do first order perturbation in the Hamiltonian, and you want to find first order perturbation in the orbitals. This is what you're after. And in a strict formal way, you can do it with the Green's function over here. And so first you see what's going on. 0 plus first order, 0 plus first order. What is this first order? Well, it's this Green's function applied on H1 working on psi 0. And here G is made explicit by sum over all the empty states. And you can do this like this, but it is slow because you need the few Rydbergs of empty states. So 20, 30 EV above your Fermi energy. This is not nice. So what you can do is you can multiply on the left and the right hand side with this expression, the energy minus the zero order Hamiltonian. You do it on the left, you do it also on the right over here. Then this stuff starts to work on this orbital, which gives, of course, this, but H0 times this gives the energy epsilon E. So working here is epsilon n minus epsilon E divided by epsilon n minus E, which gives you the 1, which you see over here. Then it's all the empty ones. And the sum over the empty ones you can represent as 1 minus the sum over all the occupied. And now all the empty orbitals are gone from the right-hand side. You only have occupied states over here. And you have a matrix equation where you have something working on the first order orbitals is something you actually completely know. This you can solve iteratively, like on many other places in VASP, for example, with the RMM. And then you don't need all those empty states. That is the big message. The overlap story is out here. The actual thing is more complicated, but this is the idea. Let's go to the next step. The next bullet is now you have the current, and from the current, you want to go to the induced field at the nucleus. So this is your current. And then you have to apply the Biot-Savart law. That is very easy for this part because you can, this is the plane wave part. You just do a Fourier transform. Then you get Fourier decomposition of this current density. And then you do the sum, which is Biot-Savart in reciprocal space. And you do it explicitly with R here, the position you want to go back to. You can't do an FFT back with an, you have to do it with a slow Fourier transform like this, because this typically does not coincide with a grid point mesh. Then you have the one-center contributions that yield current in the PAW sphere around all three. And the nuclei at the center of the PAW sphere, of course, feels a field from that center, from that PAW sphere itself. That's the red thing, that is contribution A. And it feels a field from all the other PAW spheres. That is contribution B. And very often in practice, contribution B is completely neglected. And that is very often a very good approximation. And then you only consider the one-center corrections from the PAW sphere that is at the nucleus you are interested in. And of course, that is again important to get this accuracy and that you have this one-center corrections. Otherwise, you're making rubbish. Okay, so these are substantial one-center corrections in general. And as I already said, this B thing is typically neglected. We will talk about it in the next part, tomorrow part. There are contributions, two-center contributions, where a current in one sphere gives a contribution to a nucleus in another sphere. It's very small, but occasionally it's relevant for hydrogen shield. That's really the only case that we've seen that it can be really important. This is a pictorial explanation of the next slide, which tells you about all the contributions to the shielding for one particular nucleus. And here you see this nucleus is this dot over here. Now what is there? There is this one center corrections. That is this little current that goes around in this one center over here. Maybe I should have made that red instead of blue to be consistent with previous colors, but now here it's colored blue. That's going on there. Then there is current on the plane wave grid that flows through this and flows through the whole material. Everywhere that is flowing. That's contribution 2. That's the J bar. And then there is a third contribution that has to do with the fact that we're dealing with a finite crystallite. So the crystal doesn't go to infinity, but it's cut somewhere. Here it's cut into the form of a sphere. And that is typically what is assumed, that it is a spherical crystallite, because that gives a contribution that is uniform throughout the whole material. This contribution has to be described with macroscopic magnetostatics, and you need the susceptibility. You bring system in with a susceptibility inside a uniform magnetic B0 field that introduces a uniform field throughout the whole material that can be seen as the consequences of a macroscopic current that is induced on the surface. So that is this red guy going around over here. That's contribution number 3. It's a small contribution in total. These two guys are much bigger, but it is there. And of course, there is the external field also that is even much bigger, and which is not in these 3 contributions. So you can write it as follows. The shielding tensor that you calculate is what I've done now here. I've made it one center. and interstitial and surface. But here it's even more complicated than that, because we have the surface contribution, we have this GIPAW contribution, which is both the one-center contributions and contribution from the current flowing throughout the whole system, the soft current on the plane wave grid being everywhere. So there's two contributions, 1 and 2 over here. And we have not added yet the shielding due to the core electrons. That calculated separately and is added again to it. So we have 3 contributions that you actually see in the VASP calculation itself. Core one, the surface one, and the whole shielding contribution. And this one consists of one-center corrections and plane wave. We will come back to this contribution tomorrow. This has to do with the macroscopic susceptibility. But what is important to stress over here is that this gives a contribution that is uniform throughout the material when you are dealing with the sphere. And there are other forms in which it's also uniform, but it is not necessarily uniform in an experiment. There can be variations depending on the shape of the particles that are in there. So now something new. Now something which is in progress. We want to extend this to systems in which the nuclei are becoming heavy. If nuclei are becoming heavy, we know you come deeper in the periodic table, the spin-orbit interaction becomes stronger. When the spin-orbit interaction becomes noticeable, then when you have an external magnetic field and the spin-orbit interaction together, you get more things going on. You don't only have orbital currents, as we have seen flowing in the previous story, but you also get an induced magnetization density in the material, which is manifested as a kind of hyperfine-like interaction. And that you also want to have in the PAW method. So what you have to do then, first of all, you have to choose some approximated theory for your relativistic effects. And then your Hamiltonian is going to change a little bit. And the red part over here is what is going to change. There is a K factor here in the kinetic energy. You see this is just what we had previously, P plus A over C, and it is squared and divided by 2. This factor comes in. And here you get the spin-orbit interaction, which is this K squared over here, and the gradient of the potential. And here you get the Zeeman term. This is the external field interacting with the spin density. These are the Pauli spin matrices that you see over here, which also come into the Hamiltonian. It's the Zeeman energy. It's spin Zeeman energy. This really is the orbital Zeeman energy. And this K factor depends on the potential. That's a radial thing. When you come very close to the nucleus, it becomes noticeable. If you are far away from the nucleus, then V is small relative to the velocity of light. It's 1. You don't notice this at all because this thing over here is just 0. But once you get close, say 10 to an angstrom or so, this thing starts to become noticeable. Okay, this is the ZORA approximation, zeroth order regular approximation. This is what we choose to follow. Of course, you can do something else, but this is very natural because in VASP you have a 2-component ZORA-like spin-orbit interaction already present that you see over here. This one now in PAW language, and this goes into the unperturbed problem. So in the self-consistent calculation you do before applying the magnetic field, there is no field here, you just apply this one-center spin-orbit correction. And you see here it has no plane wave contribution because it is essentially cancelled, completely cancelled by the pseudo partial wave contribution that you would have over here, because this operator is localized. It's very close to the nucleus where it is imported. And so this makes this a little bit simplified. You only have projector functions and you have the matrix element with partial waves. Now you can look over here if you want to know more details. Okay, so that's the zeroth order perturbation. And then your first order perturbation, well, I haven't shown it before, but in the HPIC and Maori, this is the zeroth order, this is the first order perturbation. You now get more. You get the spin Zeeman over here on the plane waves and operating as one center corrections. And you even get a little bit crazy terms over here that I don't bother to write down at the moment, but these are small. Now the unperturbed problem, you still don't have any spin polarization. It is just an insulating system. There is no magnetic field. You have spin orbit, but there is as much spin up as spin down density everywhere in the system. But the moment you put in this Zeeman, then you get the spin density fluctuation. You get finite magnetization density in the material, and that is also occurring at the positions of the nucleus, so where you want to calculate your shielding. And this magnetization, that gives, in a formal sense, rise to an additional current. And that can also be seen, instead of as an additional current, as an hyperfine interaction, magnetization interaction with the nucleus. So that is on the next slide here. Here you see the current density in a formal sense. This is what you already had. This is the paramagnetic current. This is the diamagnetic current. And now we add spin current, which here is measured with the Pauli spin matrices. And you get a K factor because it is zero up front. And the spin current gives rise to a dipolar field. This is this S, which you see over here, the spin density that is measured over there. And if you do lots of calculus, you can see that is actually this whole story, this red story over here, gives rise to an additional magnetic field at the nucleus, which is due to the induced spin density. You see it over there, which has a dipolar form. This is this form, these two blue things over here, and Fermi contact contribution, which is the red thing over here. And this Fermi contact contribution is a complicated guy, because here you see a delta function, but it is not really a delta function. It is a smeared out delta function that takes into account the shape, the S-type orbitals near at the nucleus. But it's also too much detail now. I'll just go to the next slide. And the next slide shows a few calculations that we did to test this. It's implemented, but it is not yet in the release at the moment. First, let's have a look at how chemical shielding and chemical shift are defined. We should talk about this tomorrow. This is a little bit of an error of me, but the chemical shift is minus the shielding. And for heavy nuclei, this is an approximation. It's not completely true, but if you plot shift against shielding, it's almost slope -1. And here you see calculations. Over here you see the experimental chemical shift, this guy. Here you see the computed shielding, that one, but there is some offset in between. The point is now that we want to have a slope that is almost -1. Then we're doing a good job. That this against that is -1. There are, here you see the systems that we considered for this test. It's all red, it's very heavy nucleus. There are cluster calculations of that in the literature, where with ADF, people make a cluster representing the bulk of the system. This cluster can consist of a number of shells. Here they have done 3 shells, 5 shells. And then they find with 3 cells the red dot, and when they do a better job with green, with 5 shells, you get the green dots over here, and that are the calculations. But what we now are doing here, we're not doing a cluster calculation. We're doing it now with a real crystal calculation, where we have added the terms discussed in the previous slides, and then we get the black dots over here, which is pretty good. Over here we get to the values of the ADF calculations over here. And over here there are some, you have to worry about the assignment. If you do this as we think, it gets well. Yes, so this is new, which is not yet in. We hope to have it in very soon. There are also some problems here, and I'm not going to talk about that because it goes far too far at the moment. You see here is part 2, which tells you that now 1 is finished. And this means I have to give the word again back to Christopher.
Yes, I am. Thank you very much for the talk, Gilles. It was really brilliant. It connects a lot of areas nicely together. Thank you very much.